So, welcome to Lecture 34. So in the last week of this course, we will go over some of the results that we discussed in the context of equivalence relations. So let's talk about that. So, equivalence relations. So recall a relation on a set X so denoted tilde, so we can use the tilde to denote the relation. And so first of all, the relation is technically is a subset of pairs. So R is a subset of the product of X with itself, and we say X is in the relation to Y means that the pair XY is in the subset R. It is just technically to make sense of what it means to have a relation on a set. It's actually just a subset of X cross X. And so once we have this, then if I have a pair XY, it can either be in the subset R, in which case we write X is X tilde Y, or XY is not in the subset R, then X is not in the relation to Y. So a relation is an equivalence relation if right, it's we have a symmetric sorry, I forgot the reflexive. They're always written in the correct order. Reflexive means X is equivalent to X for all X in the set. Symmetric means that X is equivalent to Y, implies Y is equivalent to X. And transitive, X is equivalent to Y, and Y equivalent to Z implies X is equivalent to Z. So those are the three properties: reflexive, symmetric, and transitive. And for X in the set X, for an element in X, we write like this, square brackets X. This is the set of all Y in the set such that X is equivalent to Y. And this is the equivalence class. Of the element X of the set X. And so if tilde is an equivalence relation, then we have the following facts for the equivalence classes. So every X in X is contained in an equivalence class namely, it's contained in its own equivalence class. X is in X because the relation is reflexive. X is equivalent to itself, so X is in its own equivalence class. This is the first fact, and the second fact is if you have two equivalence classes, X and Y, there's only two possibilities. If X and Y are equivalence classes, either the intersection of the two equivalence classes is empty, or the two equivalence classes are equal. so X decomposes into equivalence classes. So what would we say? So this fact here, this follows from the three axioms: reflexive, symmetric, and transitive. What you have to show is that if the intersection of two equivalence classes is not empty, so if you have a Z in X and a Z in Y, then you have to prove that the two equivalence classes are equal. And that's not hard to do. Let me skip the proof of that, though. It's a bit boring. And so there's various equivalence relations on matrices and on linear maps. So let me go back to the first example that we already covered in the first week of this course. And there the set X was the set of matrices of a fixed size with coefficients in a field F. So m by n matrices with coefficients in a field F. And the relation is row equivalence. Means right, that A is two matrices are equivalent if I convert one of them into the other by a sequence of elementary row operations. And we had already seen back then that that was an equivalence relation. And we had also characterized it, described completely two facts. So first of all, when are two matrices row equivalent? So A is row equivalent to B if and only if I compute the reduced row echelon form of A and B, they are equal. So we have a very good criterion to tell when two matrices are equivalent, when two elements are equivalent according to row equivalence. The second fact is also a good description of the equivalence classes. So in some sense, a good overview of the equivalence classes by the fact that every equivalence class contains a unique matrix in reduced row echelon form. So we know exactly what all the equivalence classes look like. So we have first of all a good criterion to check when are two matrices equivalent. And secondly, we have a good description of all the equivalence classes. So that's in some sense the best we can hope for this classification of matrices up to row equivalence. Now, the textbook describes another equivalence relation on matrices, so which they just call equivalence. So another example is where X is again the m by n matrices. So sorry, there's something I had to say for this example. That in fact, what's a way to I mean, so let me just remark that A is row equivalent to B if and only if there exists an invertible matrix P, so this is an M by M matrix, such that A P is equal to B. All right, let me just review why this is so. I mean, if A is row equivalent to B, then we can accomplish these row operations by multiplying A on the left with elementary matrices. And so then we take the product of those elementary matrices to give us the matrix P. And then, so that shows that if A is row equivalent to B, there exists such a matrix P such that PA is equal to B. Conversely, if PA is equal to B for some invertible matrix here, then you can write this invertible matrix as a product of elementary matrices to see that actually that you can convert A into B by elementary row operations. I think we had also gone over that before. So this is in formulas a way to say what it means for the two matrices to be row equivalent. So now let's talk about the second example. Again, we're talking about M by N matrices with coefficients in the field F. And now we say that two matrices A and B are equivalent if there exists a diagram like this. So let me draw the diagram. Sorry, if A is an M by N matrix, it describes a linear map from Fn to Fm. Similarly, B and I should probably have written, let me just, let me write Q here and P there. So if there exists, so A and B are equivalent if there exists Q, an N by N matrix, and P, an M by N matrix, both invertible, such that this diagram commutes. And so this says that, well, we can say, for example, that B is equal to, first we do Q, then we do A, and then we do P inverse. Well, or equivalent, we can write this as A is equal to first Q inverse, then B, then P. We can think of this as an instance of we start out with some generic general linear map from Fn to Fm, and maybe we can find a suitable basis in the domain, with this canonical basis isomorphism, and another basis in the codomain, such that the matrix of this linear transformation with respect to the new basis is simpler than the original one. And so the two matrices are equivalent if they're related by a change of basis. In other words, if that's one way to say it. Another way to say it is, of course, that so if I can get from B to A by multiplying on the left with an invertible matrix, that means I'm doing some row operations on B, but then I'm also multiplying on the right now with an invertible matrix. So I'm also doing column operations. So A is equivalent to B if and only if A can be converted into B by a sequence of elementary row and column operations. So previously, I was only allowed to do row operations, and then I was trying to find a matrix, a row equivalent matrix, which was as simple as possible, and that was the matrix in reduced or echelon form. But now if I'm allowed elementary row operations and column operations, then of course, so every matrix A is equivalent to a matrix like this, where I have just an identity matrix up here in this corner, and otherwise I have nothing but zeros. And of course, neither row nor column operations ever changed the rank of a matrix. So the size of this matrix here is the rank of A. Right, that's fairly easy to see. You can do row operations to put the matrix into echelon form. So you have still some junk here that you don't know what it is. You can do column operations first, swapping all the pivots to the front. So then the pivots are at the top and at the front. So the pivots are exactly here. And then you can use the pivots. You can do sort of a backward substitution for rows instead of columns. So use this one to get rid of all those entries, this one to get rid of those entries, and so on. You can clear all those entries there. And so so the theorem you can deduce from this is that so A is equivalent to B if and only if rank of A is equal to the rank of B. So that's, according to this equivalence relation, the way to tell whether two matrices are equivalent. That's the first fact. And the second fact, again, how do we describe all equivalence relations? So the equivalence classes, so every equivalence class well, maybe I should say this. There are I don't know. So here, in some sense, here's a list. So we have the zero matrix. Then we have a matrix with a 1 here, and then 0, 0, 0. Then we have a matrix with and so there are, this is a complete list of the equivalence classes. So here's the, well, and this goes until K is equal to the smaller of M and N. We can also even a version of this for linear maps. So if, say, if, so say F is equivalent to G if there exists a diagram like this. So if there exists isomorphisms then again F is equivalent to G if and only if the rank of F is equal to the rank of G. Moreover, for every linear map, so we have a linear map F from V to W between two vector spaces, you can find a basis of V and a basis of W, such that, so here's phi and there's psi, those are the canonical basis isomorphisms. And so here is the corresponding matrix of F with respect to those bases. So for every linear map F from V to W, there exist bases of V and W such that the matrix of F is as described. So it's an identity matrix of size, the rank of F, and then it's got zeros elsewhere. And so, I mean, I've already proved it because every fact about linear maps is a fact about matrices once I choose bases. But I can also go over this proof again. We had proved this in when we had proved the rank nullity theorem. So you can you can prove this as follows. So choose first a basis of the kernel of F. So let's say that's W1 through W. So let's say Wn minus R. So let's say R is the rank of F. But then we know that and if the dimension of the domain is n, then the kernel has n minus r, dimension n minus r. So if we choose a basis of the kernel of F from W1 to Wn minus r, then we complete this to a basis of V. So let's call those elements V1 through VR. And then we had seen that V1, so then F of V1 through F of VR are linearly independent in W, and then we can complete these to a basis with some more vectors. So I don't know, y r plus 1 to y m. And then if we write down the corresponding matrix with respect to the basis we had chosen, so let's say we take V1 through VR and then W1 through Wn minus R, that's our basis of V, and of W we have F of V1 through F of VR and then YR plus 1 through YM. If we write down the corresponding matrix, Well, we have to see what F does to the basis vectors. Well, into V1, it maps F1. So writing F of V1 as a linear combination of these guys gives us 1 and then nothing but zeros. Right? For V2, we get F of V2, so we get just 1. You know. This continues. VR gives us F of VR. These were all in the kernel, so they all get mapped to 0. So we see that choosing the basis in this way, that was used in the proof of the rank nullity theorem, actually gives us bases for V and for W such that the corresponding matrix has this form. Okay, so right, and just to remind ourselves, right? So the first example was row equivalence, where two matrices who are equivalent if I'm allowed to multiply on one side, on the left side, by a matrix. That was classified by the reduced row echelon form, and if I'm allowed to multiply in the left and right, I get just the rank. That's about general matrices and general linear maps. Now we specialize to endomorphisms. So now we're looking at linear maps from a vector space to itself, not from one vector space to a different vector space, but a vector V to itself. And then, of course, it's natural to to take only one basis for V, right? In the previous example, for the equivalence of matrices, I was allowed to take one matrix for V given by this, one basis for V given by phi, and another basis for W given by psi. And that gave this very simple classification in terms of the rank. So now we say, so let me do the matrix version. So now we're talking about square matrices because they represent endomorphisms. So let's say n by n matrix. And now the equivalence relation is called similarity. So we call B and A are similar if we can draw a diagram like this. Well, let me write P now. If there exists a diagram like this, so if there exists an invertible matrix P, also n by n matrix, such that first B and then P is the same as first P and then A. Oops. So A is equal to P, B, P inverse. Yeah, first P inverse, B, and then P. Right, so in this case, the matrices are similar, so they're equivalent. If I can get from one to the other by multiplying on the left and right with the same matrix. I'm not allowed two different matrices, but they have to be the same matrix. So this is the kind of situation we were considering when we had an arbitrary matrix, square matrix, and we were trying to diagonalize it. Then we were trying to find a diagonal matrix B such that we were doing this, or in the general, for the general endomorphism, we were trying to find one single basis of the endomorphism, right, making the corresponding matrix as simple as possible. And if F was diagonalizable, then we got a diagonal matrix A. And so, so here it's actually, the description is not at all as simple as, so here's, it's actually quite hard. To decide when A is similar to B, or to describe all similarity classes. Right, the similarity classes are the equivalence classes according to the similarity relation, which of course similarity is an equivalence relation. So let me say first of all, though, that if A is similar to B, then these two matrices have the same characteristic polynomial. Then also they have, in particular, they have the same determinant. And right, the whole point of changing basis like this was to compute the eigenvalues and find eigenvalues and eigenvectors, and the whole point was that the eigenvalues didn't change when I went from one matrix description of the same endomorphism to another. So, right, we can see this easily. So if A is equal to P, B, P inverse, then the determinant of A minus T times the identity matrix is equal to the determinant of P, B, P inverse minus Ti, which is equal to the determinant of P, B, P inverse minus P, Ti, P inverse. T is just a scalar, doesn't matter where I write it, and so, and P times P inverse is the identity matrix. And then I can write this as the determinant of P and B minus Ti times P inverse. Right, if I multiply this out, I get two terms, P, B, P inverse, and P, Ti, P inverse. And by the multiplication formula for the determinant, I get that this is determinant of P times determinant of B minus Ti times determinant of P inverse. And then these two determinants cancel because now these are numbers which commute with each other. Before, when I had matrices, they did not commute with each other. But elements in the ground field do commute with each other. So we see that the determinant of A minus Ti is the same as the determinant of B minus Ti. So we see that certainly the classification up to similarity for matrices is more complicated because it's at least as complicated as all the possible characteristic polynomials that you can write down. And so we will just talk about the Jordan canonical form So this answers the question, so the question of the describing all similarity classes of matrices. So answers the question how to describe all similarity classes. Over the complex numbers only. So this works only so if the ground field is not C, then things get a lot more complicated. I mean, of course, the reason is that over the complex numbers, our characteristic polynomial we will decompose into linear factors. If the field is not algebraically closed, if the field is not C, then the question is additionally complicated by that fact. So, so let lambda be in C, and then we consider a matrix like this, lambda. So it's all lambda on the diagonal. It's all 0 below the diagonal. There's ones in this so just one step up from the lambdas, and then there's zeros again. So this is a so-called Jordan block matrix. Right. So, for example, if I just have a 1 by 1 matrix, this is a 1 by 1 Jordan block. 2 by 2 Jordan block looks like this. 3 by 3 Jordan block. Etc. And so, so the characteristic polynomial of the Jordan block, right, is let's compute it. So lambda minus t is on the diagonal, and then there's a bunch of ones. You compute the determinant of that, so that's just the product of the diagonal terms because it's an upper triangular matrix. So this is lambda minus 1 to this k, say, where k is the size of the Jordan block. So lambda is the only eigenvalue. So there's only one eigenvalue. So, and of course, we see from the characteristic polynomial that this has algebraic multiplicity k. So what is the geometric multiplicity? So what is the eigenspace? Well, that's the null space. So now I have to substitute for t lambda. So that means I have now zeros along the diagonal, zeros here and ones up here. And so I see that this matrix is already in reduced to echelon form with one free variable, namely the first row corresponds to a free variable. So, so the null space is one-dimensional. So eigenspace, so the dimension of the eigenspace is equal to 1. It has to, of course, be every eigenspace has dimension at least 1. That's always the case because it's an eigenspace, so there exists a non-zero eigenvector. But in this case, it's not any bigger. So in some sense, this is like the most undiagonalizable such a matrix can be with only one eigenvalue. So Okay, so that's the Jordan block. And so the theorem, which we will not prove, it's quite a difficult theorem, is that every every matrix A, a square matrix with complex coefficients, is similar to exactly one matrix. Sorry. That's not quite the way I should say this. Just check. What's the best way to say this? Well, maybe first just write every matrix is similar to a matrix in Jordan canonical form. Which means it consists of, i.e., it is block diagonal with Jordan blocks on the diagonal. So, so there's there's a Jordan block with, well, maybe I should have given this Jordan block here a name. So this is maybe, let's call this matrix here J sub lambda upper K. So K is the size of the matrix and lambda is the eigenvalue it has. So there is some J lambda 1, K1, J lambda 2, K2, J lambda R, KR. So all these blocks are on the diagonal, everything else is 0. So for example, if all the Jordan blocks have size 1, then the matrix is diagonalized, then A was diagonalizable. So if A is diagonalizable, then its Jordan canonical form is a diagonal matrix with the eigenvalues on the diagonal, and all the Jordan blocks have size 1. But if A is not diagonalizable, of course, you can't put it in diagonal form, then this theorem says that at least you can still put it into a made form with all these Jordan blocks. And of course, this Jordan canonical form is not unique because like even if the matrix is diagonalizable, you have a choice in which order you write the eigenvalues, right? So you could swap out the order of your basis of eigenvectors, and then you get a different diagonal matrix. If you're talking about real numbers, you can say we can order them by size, but these are now complex numbers, these eigenvalues, so that we can't order them by size. So there's not a good way to make it completely canonical. So we can then say, as a second part of the theorem, that so the Jordan canonical form is unique up to reordering the Jordan blocks. Okay, so that's the theorem about Jordan canonical form. we can write this, what this says for endomorphisms. So this says, so let f from V to V be an endomorphism of C vector space V, right? Then there exists a basis B of V such that the matrix is in Jordan canonical form. Yes, and you can similarly write down in a relation, an equivalence relation, calling to endomorphisms similar if if they have similar matrices, etc., and you get the classification in terms of Jordan canonical form. Okay. So let me just finish by just just a very simple example to say, so, well, no, let me just, no, I think this lecture has been long enough, so let me stop here and continue next lecture. Thanks for listening.